All right, let's dive in. Today, we're tackling one of the coolest challenges in AI. How do you take a massive, absolutely enormous model and teach it a new trick without having to rebuild the whole thing from the ground up? It's a question that really gets to the heart of making AI smarter, faster, and honestly, more accessible for all of us.
So let's start with a number. 175 billion. That is the number of parameters in a single model like GPT-3. You can think of parameters as all the little knobs and dials that an AI can tune to learn something. And it's this sheer scale that makes these models so incredibly powerful, but it also creates a gigantic problem.
And that right there brings us to the core issue, what I'm calling the billion parameter problem. I mean, think about it. When you have a model with 175 billion parts, how on earth do you customize it for something new? How do you teach it to be a legal expert, or a creative writer, or a medical chatbot, without, spending an absolute fortune on computing power?
Well, the traditional way is something called full fine-tuning. And what that means is you adjust every single one of those 175 billion parameters for each new task. The analogy here just nails it. It's like needing a slightly different car and deciding to build an entirely new 100-ton engine from scratch. Every single time. It's just unbelievably inefficient and expensive.
And this table really shows you just how massive the difference is. Look at this. With full fine-tuning, you're training all 175 billion parameters. That takes up about 350 gigabytes of storage for one task. But with efficient fine-tuning, you're training less than 0.01% of the parameters, and the storage plummets to under 100 megabytes. I mean, that's not just an improvement, that's a completely different ballgame.
So how did we get from that massive problem to this incredible solution? Well, enter our first hero of the day, a technique called LoRA. It was a breakthrough that really changed everything.
So LoRA stands for low-rank adaptation. And the core idea? It's brilliantly simple. Instead of changing the entire model, you freeze it. You don't touch any of the original 175 billion parameters. Then you inject this tiny pair of new trainable layers, or matrices, that learn all the changes for the new task.
Now, this whole technique is based on this fascinating insight from the original LoRA paper. The researchers basically guessed that even though the model itself is crazy complex, the updates you need to make for a new task are actually really simple. They have what's called a low intrinsic rank. In other words, you don't need a sledgehammer to make a small adjustment, you just need a really, really precise screwdriver.
So let's go back to our car analogy. If full fine-tuning was building a whole new engine, LoRA is like adding a small, super efficient turbocharger. You keep the original engine, but you bolt on this tiny, powerful part that gives you the performance boost you need for a specific job. It's just elegant and so effective.
Okay, so how does this magic trick actually work under the hood? Well, it's surprisingly straightforward, actually.
Okay, here's how it goes. First, your input, let's call it X, goes through the original, massive, frozen part of the model, business as usual. But at the exact same time, in parallel, that same input also goes through your two new, tiny, trainable matrices. And then, at the end, you just add the results from both paths together. That's it. You're not changing the original path, you're just adding a tiny corrective signal right alongside.
And the results are, well, they're staggering. The first huge benefit, LoRA can slash the number of trainable parameters by a factor of 10,000. We're talking about going from billions of parameters down to just a few million.
And next up, it lowers the barrier to entry for everyone. LoRA can cut the GPU memory you need for training by up to 3 times. This is huge. It means more researchers, more developers, even hobbyists can now afford to train and experiment with these giant models.
And here's the kicker, the real mic drop moment. Because these little update matrices can be mathematically merged back into the original frozen weights after you're done training, LoRA adds exactly 0 extra delay or latency when you're actually using the model. It's just as fast as the original. This is a massive advantage.
LoRA is incredible for sure, but the story doesn't end there. The next step in this evolution is a technique called AdaLoRA, which asks a really important question.
This quote from the AdaLoRA paper just frames the next challenge perfectly. LoRA is fantastic, right? But it kind of treats all the parts of the model it modifies as equally important. It gives the same update budget, so to speak, to all the different weight matrices it adapts. Which, of course, leads to the natural question, what if some parts of the model are way more important for a new task than others? Could we be even more efficient by spending our limited budget of trainable parameters more intelligently?
Let's go back to our analogy one more time. If LoRA is a turbocharger,
Think of AdaLoRA as a smart turbocharger. It doesn't just apply the same boost everywhere. Nope, it analyzes the entire engine in real time and dynamically sends power only to the parts that will give the biggest performance gain. It wastes absolutely no energy on parts that just don't need it.
And this slide just lays out the difference perfectly. LoRa's philosophy is all chosen parts are treated equally. It spreads its budget of trainable parameters nice and even. AdaLoRa's philosophy is different. It says some parts are way more important than others for this specific job. So it actually calculates an importance score for each matrix and gives more parameters to the high scorers.
And this chart shows you exactly what that looks like in the real world. AdaLoRA might figure out that for a certain task, the query and value weights are absolutely crucial. So boom, it gives them a bigger chunk of the parameter budget while giving less to the key and output weights that it decides are less important. It's a surgical, data-driven way to be efficient.
Okay, so we've seen some really clever engineering here. It's cool stuff, but why does any of this truly matter in the real world? What's the big picture here?
Well, in short, techniques like LoRA and AdaLoRA are basically democratizing AI. By slashing costs and hardware needs, they're letting smaller teams, universities, and even individuals work with the best models out there. This means you can build tons of specialized AIs on top of a single base model, saving huge amounts of storage and energy. And honestly, it's just a greener, more sustainable way to develop AI.
This summary table really puts it all into perspective. You've got full fine-tuning at the top, super powerful, but astronomically expensive. Then LoRA comes along and cuts the trainable parameters to a tiny fraction with no added latency. And finally, AdaLoRA uses that same tiny budget even more intelligently, adaptively putting it where it counts for potentially even better performance.
So, in the end, this whole journey from brute force fine-tuning to this surgical adaptation, it's not just a technical detail. It's a fundamental shift in thinking. We're moving away from the idea that bigger is always better, and we're moving towards a future where the smartest approach is also the most efficient one. Which leaves us with one final thought to chew on. As these AI models continue to grow to sizes we can barely imagine, is it possible that the most important breakthroughs won't come from making them bigger, but from finding clever, tiny ways to make them better?